Kabam Robotics, and he will give us a keynote on navigating the wild Teleoperations role in ensuring 24/7 robot uptime. Jakub, the floor is yours.
Thanks, Carol. Thanks for the introduction. Actually, clarification on that. So it's engineering director. So I'm the tech guy in the company. So expect more of a technical presentation, not sales pitch. Although there are some let's say product slides because I feel that I need to introduce what we are building before I can get into the fun part about teleoperation and robot operations. Sorry about the dizziness. My camera on my laptop is not working, so I'm using the conference camera. I might be rotating a bit. I still feel that I should be showing my face, but let me know if you are dizzy. You can turn it off. I also wanted to make it more fun, so there is a demo as part of this. Carol, please cut me off at the 15 minutes in case I somehow overrun or get stuck on anything not important. But as Carol introduced me, my name is Jakub. I'm the engineering director at Kabam Robotics. And today I'm gonna talk about robot operations. I'm particularly gonna focus on teleoperation and expand on how we actually how we use teleoperation to keep our robots up and running. So we are a startup based out of Singapore. We provide cloud robotic solutions, mainly tailored to security industry, but also facility management industries. We started building robots 3 years ago and never stopped really. But yeah, if you've been in Singapore in the past 3 years, you probably interacted with our robots. We have them, in some of the nice sites. Some of you might recognize the Marina Bay here. There's the airport. Some of the parks. This is the flywheel. So most of our robots are currently in Singapore, but in the past 6 years, the team has been focusing on really expanding across the world. So now we have footprint in Australia, in Hong Kong, in Taiwan, in Japan, in the US, which is probably our next major market. And recently we delivered also in Chile. So that's why I can quote the four continents, but still the majority of the robots are in Singapore. I think this world expansion is also creating some interesting challenges in terms of the latency that I may talk about in the presentation. To introduce a bit more of what we are building is both hardware. So we built our security robots, and you can see some of them behind me. So those are our collabs, the indoor security robots. But we also built a cloud robot platform for robot operations and robot management. I'll just briefly introduce the two robots that we are building. So this is Collab. It's an indoor security robot for security and concierge features. Typically, it would be deployed in places or facilities like shopping malls or hospitals. So with that in mind, it was designed more friendly. Kids, like to jump on it and hug it. Also because it's deployed in places with crowds. Hoarding is an issue, so we also deploy this boom. Like it just goes up and down, and there are cameras on top. We recently also launched Halo. It's our outdoor security plus patrolling robot. It's a skid steer, and it's built to be weatherproof, particularly for Singapore. But recently we've been deploying in places. So Singapore weather is lots of rain, lots of humidity. Recently we've been exposing it also to -10, -20 degrees. So we are trying to expand the range of where the robot can go. As compared to Collab, the design, the key idea for the design was deterrence. And some of you may pick up, or I hear it actually often, that this looks a bit like the Tesla track. I like to say that we've been there before, Tesla track, with the design. But yeah, it's more edgy and supposed to deter people. It's deployed in public parks. Does permit to patrol around large facilities like airports, for example. And the third product that I will be focusing on the most, and this is actually how we started the company. So we started building Smart Plus, what at the time was Smart Plus, in 2018, 2019. We were called Cognicept Systems at the time. And we were running operations for a company called Saviok. Some of you may have heard of it. It's one of the below garage companies, one of the original robotics companies. Now they are called Telerobotics. And I think we picked up a lot and learned a lot about the robot operations and what needs to be done for them. And for that, we built this platform. And from the beginning, it was really focused on robot operations. And it was built to be simple, really, for any kind of user to just jump in and intuitively use robots. So you don't need to be trained robotics engineer. Now we also have a mobile app, so the same kind of things you can do with the desktop interface. You can also use a mobile app. One of the things that we didn't appreciate initially was connecting the same this platform into existing systems, and this is actually what's really propelling our growth now with the security customers really wanting to also integrate with our robots with their existing systems. The main thing I really want to talk about is the observability and remote intervention capabilities that were originally the idea of why we were building this platform. Yeah, it has much more things. I had this video, but I think since this is a remote meet, I can also give a quick demo. So I have a robot here in the office. This is Collab. It's our testing robot. This is our dev platform. So also, if something doesn't work, I'll switch back to the video as Marv is. As Marv may not be kind to me. So you are looking at the indoor security robot. Right now I'm in the same room, but really this robot could be across the world. I'll be seeing the same thing, just probably with higher latency. I'll send the robot to look at the workshop. So yeah, here on the top left, you see the live video stream of what the robot is seeing right now. You see the path plan that's generated by the navigation system. You see the point cloud. You see the LiDAR map. So as I was showing before, the robot has a boom. So from here, I can just boom up. The boom is going up, so I can see what's happening in this other production area. And if I actually increase the resolution, yeah, so there's bunch more collabs here. There are some production for halos happening here. Of course, this is typically autonomous, but sometimes the robot gets into troubles, and I'll try to demonstrate a little bit stupid demo that I came up with a few minutes ago. So I'll try to send it across the office. Let's say here. Once the boom goes down. So I saw that there's this cardboard box that I can see also in the that I can see also here in the LiDAR map. So let's see if I can. So that's the main thing actually I want to talk about is the teleoperation. Let me just take over the navigation system and see whether we can push the cardboard box without doing anything too dangerous. I see I didn't do too good job because the cardboard box is still there. So let's try to push it over. Okay. Okay, so I think this worked. Yeah, so now the robot should be free to go really anywhere. So yeah, quick slide demo to show the teleoperation. And I typically like to do this before actually I dive into the deck, not at the end. And let me just go next slide. Yeah. So we've over the 3 years we've deployed more than 100 robots out there. So we have 80 robots right now live running missions at every moment. And I just put here the slide not because I want to blow my trumpet maybe a bit, but mainly I'm going to show in terms of security applications how wide range of environments we have. So those are just collabs. And really, those are unstructured environments without obvious rules. So of course, autonomous driving has its own challenges, like you are driving 2 tons at 100 miles per hour, which can be dangerous. But at least there are some traffic rules that you can encounter on the road. In these places, literally anything can happen just because you have humans. You have really changing conditions all the while. And we solve these challenges and risk operationally. And this takes really lots of humility for a robotics engineer to admit that your robots and your navigation is not perfect. But I think this was crucial for us to recognize that early on to make this success and maybe get ahead with the deployments before your navigation system is perfect. And just to show you the kind of scenarios that our robots need to tackle, we'll just show one deployment. So this is our deployment at Bedok Reservoir here in Singapore. We call this robot Oscar. We actually have 2 of them here. This is on our TikTok where they take turns in terms of patrolling. So the robots have charging stations somewhere here, and they go around this 4-kilometer perimeter just to look for things like illegal smoking, illegal fishing, people who are not supposed to be there where at some spot, and they do these regular patrols every 2 hours instead of a human. Why instead of a human? Well, humans don't want to walk in this kind of rain, for example, but the robot really doesn't mind, except that sometimes this may pose challenges for the navigation, and we might really encounter some of the strange edge cases. So normally this environment is really simple, and your navigation system should tackle it easily. But what if there a situation like this where there are folks who are cutting trees, there is a rain, there is a ditch full of water on your right side. And this is just an example of an edge case that actually this is autonomous. People are recording this video because they were actually surprised that the system was able to handle this autonomously. But sometimes we really need to jump in and help the robot to recover. A few more examples of the kind of edge cases that we can see. So here, people hogging, should our navigation system handle this this situation, or maybe can we use teleoperation for this one moment to help the robot. Another example from our CEO, he likes to use this one in his deck because he's coming from commerce space, from warehouses. Yeah, so at what point the navigation system or the autonomous system can decide, should I push this aside, should I run over? So that's what I was trying to show during the demo. And so robot operations is something that took me a while to get on, but once you start run a business, you realize every on-site intervention is very costly. Do you really want to drive 3 hours, which is our average drive in Australia to the sites that we deploy, just because of a plastic bag? And for autonomy, really the time to issue resolution is imperative, because that equals to robot uptime, and that's what the customers are paying for. So where we use Teleo right now, and that's all robot operations. So first, during deployment, when we do mapping, the navigation system, since our robots are using LiDAR-based navigation, we do teleoperate the robot to create the map. Then through the same system, instead of on-site, in hot, in the wind, we remotely also can set out the waypoints, no-go zones, update the map with just pushing the robot around with teleoperation. Second phase, after the initial deployment, where engineers would be typically on site, we have stabilization phase, where really we see lots of issues initially during the deployment, and those are fixed. But we still need to somehow help the robot to navigate those situations. So things like remapping happens a lot in the stabilization phase. Again, where we would use teleoperation instead of the autonomy. And of course, collecting the data to improve the navigation system. Then after the robot goes live, we have the 24/7 level 1 support that handles these edge cases, autonomy failures, environmental changes, or even hardware failures, right? If your wheel, if your axle breaks, can your navigation system handle that situation nicely? Meanwhile, human can probably deal with that kind of situation. And I know I'm running behind, but what I think was important to realize from the beginning where we started Cognicept Systems was how to get actually teleop scaling, because we cannot have one operator handle one robot. That's of course not scalable. So I think there were two recognitions in the beginning. Was to build a scalable solution, which for us is a web application. It could be, of course, something else accessible from anywhere. So our operators are, in India, Singapore, US, and by anyone. So the interface is very simple, very easy to use, easy to train. Training has been a big factor for us. And of course, that adds on top of the cost of the robot if the robot is complicated to use. We also introduced automated incident management. So instead of so that one operator can handle multiple robots, doesn't have to monitor each robot and what it is doing. Where basically it's kind of call center for a robot, which is a bit ironic, where the robot realizes, oh, something is wrong with me. So that's our error classification stack, which is, by the way, open source. You guys can find it. Maybe I will be sharing this deck later. That creates an incident ticket alert for an operator, and then the operator can intervene and handle the situation, or call someone on the site to help the robot to resolve the situation. I think the cooler stuff that we've been building So in terms of how to make in teleoperation safe, of course,
We have to
we don't
start wrapping up, Jakub.
Sorry?
We have to start wrapping up just for the timekeeping.
Okay. Yeah, really last slide. So we built a shared autonomy stack to make sure that our robots are safe. We've been playing with things like force feedback, although the scalability there was a bit tricky, where we use direct drive to do these more complicated teleoperations. So we have Copilot, where basically we rely on the navigation stack, and the human can intervene. Human can intervene by overriding the inputs of the robot navigation. So that has helped us to do this safer. In terms of scaling, instead of the steering wheel, we would use more, just feedback in terms of visual feedback, or just vibrations on a gamepad. That's cheaper for us. Okay. Okay, I'll skip this one. There are some thoughts I had about the dangers of using teleoperation when you're building a company. And I think the main message there is really scaling. It's easy to have 5 good operators. It's very hard to have 100 reliable remote operators. Just want to mention we are hiring in case we have lots of research topics and thoughts. So just talk to us, talk to me in case you have any ideas. With that, thanks for the attention. Sorry for overrunning on this. And yeah, if there are any questions, I'm happy to answer them in the chat as well later.
Yeah, thank you very much, Jakub. We have not that much time for the questions, but there are at least 2 in the chat. So I'll just read one from Andre, and you can answer to the other ones in the chat, obviously. So which technique of GPS SLAM harmonizing does your solution use?
Which GPS? I don't understand the term harmonizing, but if you are referring if you are referring to fusion of the GPS and SLAM, that's probably something I cannot share here in terms of the details on the navigation system, unfortunately.
There's another question from Etienne. Have you implemented your own navigation software, or do you use open source navigation solutions?
It really depends on the platform. So the outdoor navigation is something we are building ourselves, but for example, the indoor navigation is something vendor-based. That's proprietary, not trust-based. The indoor one, we are reusing a lot of open source for the outdoor navigation.
Okay, thank you very much. If there are any other questions to Jakub, please put them in the chat. And we will go to our second speaker. Let me introduce Dr. Antonia Tsemanaki from Bristol Robotics Lab. Antonia, the floor is yours. You have 15 minutes for the preso, and roughly 5 minutes for questions and answers.
Hi everybody. Can you hear me well?
Yes.
Okay. Let me just share my screen. Sorry, can you hear me?
Yes, we hear you.
Oh, sorry.
And it says you're started
to just
share.
froze.
Yeah, it looks like you started to screen share, but we don't see anything. We just see the loading page.
Yeah, that's a very inconvenient time to happen, but hopefully we'll get unstuck soon. So in the meantime, I'll just start. So I'm Antonia Domenecki. I'm a senior lecturer in robotics at the University of Bristol in the UK, and the Bristol Robotics Lab. The Bristol Robotics Lab is a collaboration between the two universities.
I'm not sure if it's just me, but I've lost audio.
I think we lost Tonya.
Hmm.
Let's give her a second to reconnect, maybe. I think Tonya has some connection issues. Let's give her a second. I'll try to message her in the meantime.
Did someone have other questions for Jakob then, if we have some time? Then maybe Jakob, I have a question for you. So where do you see the biggest application area growing for these robots?
For these robots, for us, it's really been the security industry, and we were not looking for this. I think the security industry has been looking for us in a way. There's not that many companies out there that are doing this. In the US, it's Cobalt, Nightscope, and I think this is the second big industry after cleaning. That's it. That's gonna be revolutionized by robots.
Okay.
What are your experiences with social interactions with your robots? Did you have any like cases of people, disturbing them, breaking them, vandalizing?
So I don't know how much you know Singapore. It's very rule-based country. So definitely less in Singapore. We've seen it. Well, it's been a good place to get started because of course it has its own have been vandalized. It has its own consequences in terms of publicity and media. So we were able to take certain actions. So we have basically anti-tampering, similar to what you see in Tesla, where we are able to detect this sound and alarm. That at least works here in Singapore. I think particularly as we deploy in US and Australia, it is going to be more interesting to see how people react to this in general.
There's another question from Radhika in the chat. How will the humans or dynamic obstacles be dealt with for Kabam robots?
Well, absolutely. Humans absolutely avoid. I don't think we've overrun anyone. And I hope that never happens. I think also one of the advantages of doing mobile robots in those kind of environments is, the safe thing is to stop in general. So if you don't know, you can stop and then ask, human operator, which is not the luxury that autonomous cars have. The decision needs to be made immediately. Generate dynamic obstacles is something that we are building into our outdoor system, outdoor navigation system, particularly for problems like road crossing. So we do need to interact with vehicles and other humans in there. So even prediction where human will be or where car will be becomes important, although it's not as important for our indoor applications.
Are there any other questions to Jakub? I haven't seen Tonia rejoining yet, and I didn't hear anything from her. So she clearly has some connectivity issues. Any other questions to Jakub? Okay, so while we are waiting for Tonia to hopefully join us again, I will make a slight agenda change, and I can bring up with Alois and Daniel a couple of the topic group updates. So as I mentioned in the beginning, the topic group is open for the participation, even if you're not euRobotics member, which we recommend to look at. You are free to participate in the topic group activities. There is a couple of updates really. Probably the most important, and hopefully most of you, if you were on our mailing list, you hopefully heard that already. From the 1st of January, euRobotics created a new portal for the topic groups that's based on the open social platform. Daniel just put the link in the chat. If you are on our mailing list, you should already get an invite into it. The portal has been set up quite well, and it should be a primary source of communication and debate for all the topic groups in euRobotics, obviously including ours. So if you haven't seen the portal yet, or didn't get the invite, or you're not on the mailing list yet, just please let us know here in the chat, either directly to one of us or publicly. Leave us your email details, and we are happy to add you to the community. The other update that I think was communicated earlier as well, we are a couple weeks ahead to European Robotics Forum. That's our annual euRobotics in-person event that takes place this year in Rimini on the 11th, 12th of March. That's where the conference starts, and our topic group has a workshop session like every year for the last couple of years. I think it's on Thursday morning, where we'll have a couple of interesting presentations. The topic of the workshop is very much about the cross-sector collaboration for telerobotics, and we'll have speakers from European Space Agency, DLR, and Jacobs Engineering. So we have a 90-minute workshop with a couple of presentations, and then panel discussions with our speakers. So if you didn't thought about joining ERF yet, please consider it. The registration is open. It has been open for a couple of weeks. Or if you would like to get any more information about the conference or the workshop itself, please let us know. I see that Tonia joined us again, which is perfect timing.
I'm so sorry about this. I had to restart my computer. It was completely frozen, so that takes a while, and the presentation seems to still, be opening now.
No worries. I switched the agenda a little bit, just gave a couple of topic group updates. So if you are
I'm afraid that
go,
once I
yours.
try to share again, I'm afraid that it's going to happen again. So I'm not really sure what the solution is at the moment, because I don't have another computer with me, and we also don't have that much time left. I'll try, and then if it gets frozen, maybe we can do it another time. And huge apologies for this.
No worries. Let's give it a go.
Okay. I think you can actually see it. Can you not?
Yes, we can see you and hear you, and we can see the
Oh,
presentation. That's
good.
great.
Okay, so yes, so this is what the Bristol Robotics Lab looks like on the left, on the outside in the night, and on the right picture is a picture of Bristol on a beautiful sunny day. So in the Bristol Robotics Lab, I lead the dexterous manipulation and wearable robotics group. And this is a cloud of words of what it is that we're doing. So we're focusing a lot on hands, haptics, teleoperation. Applications are surgical, medical diagnosis, as well as nuclear and space technologies, because we found that there's a really, really big overlap among these applications. And this is what we are exploring now, how we can have fundamental technologies that we can transfer from different application to different application. So, and of course, I'm focusing on the dexterity and especially the hands, because I don't know if you have seen these images before. This is, they're called homunculi, and it's basically the larger the part on this body it is, the more of a function it has. So for example, the left one is a motor homunculus, the sensory homunculus is on the right side. And you can see on both of those, hands are playing a really, really big part. And we know this, of course, from our everyday life, playing since we were babies, playing, touching each other, feeling each other, communicating with our environment, of course, in really high precision activities as surgery or playing the piano or cooking as well. So just want to show you a very high level overview of some of our projects, starting with some of our surgical projects. So this is back in 2016. Actually, it's quite an old project, but this is a little bit of the basis of how we have then started developing different things. So this was aimed at minimally invasive surgery, and we wanted to revolutionize basically how minimally invasive surgery is done without needing to use the Da Vinci console and sort of joystick manipulation. We wanted to have a direct sort of natural, if you like, teleoperation using your hands as a surgeon to try to minimize the time that you have to train on the system, to make it more ergonomic and generally adapt the system to your hand, not your hand to the system. So this basically included a hand exoskeleton that can track your hand and all the joints and how it's moving, and then transferring that to a little surgical instrument, in which we had here a prototype. On the left, you can see it's a 3-finger miniature hand or a 3-finger instrument with as many joints as your human hand, so that it can behave in the same way. So you can see the concept in the simulation of how it enters the abdominal cavity, deploys itself, opens, and then it is teleoperated directly by the surgeon's hand. So more a little bit on the exoskeleton, you can see how a few of the prototypes here, there are 4 different prototypes in this slide. Some of them have only Hall effect sensors. Some of them have IMUs and Hall effect sensors. And we try to incorporate also haptic feedback into these via the form of cable-driven mechanism and pulleys directly on the exoskeleton. We are also now working on soft versions of them without the 3D printing, just basically soft materials, either fabric, leather, or even silicone, that we can laser cut and make it custom made for your hand directly, because all of us have different hand sizes. So more on the now tactile and haptic side of things. This is where we started in 2018, actually. We made this little device, we call it fingertip haptic device, and it was all about having this little inflatable pillow touching your fingertip and inflating, deflating, simulating different stiffness, and also squeezing your fingertip or releasing it. And with these 2 modalities, we were able to simulate different hardness, if you like, of possible nodules when you're palpating a body, to try to, in a teleoperated way, diagnose someone if they have a lump on their breast or other parts of their body. But of course, this has applications in many more than just diagnosis here. But we took it a little bit further, and we said, okay, so this inflation and deflation gives us something, and it gives us the possibility of basically tuning the sensitivity of that device. So here we took it to make it a tactile sensor. So You might have heard of a sensor called Cactive that's been around for probably more than a decade, coming from the Bristol Robotics lab originally. It basically is a elastomeric membrane that you can see here. You print it like this, and then you flip it inside out. And then you can put a camera to monitor those dots and see how they deform when the outside of the membrane touches an object. So we took that a little bit further by making it pneumatic. We added basically a camera and also an area that is filled with air, so you can inflate and deflate. And by doing that, we were able to tune its range and sensitivity. So when you want to sense something that is beneath the surface by a lot, so like 30 millimeters, you can inflate it, make it more stiff, the membrane, and therefore have the capacity to measure something with so higher forces deeper. If you want to measure something that is on the surface on the top of the object, the surface of the object, then you don't have to have it very inflated. You can have it softer membrane, meaning then that you have a smaller range of what you're sensing, but with higher sensitivity. And then instead of having it with visual like this, where the camera has to be inside the sensor, we took it then a step further. So we removed the camera from inside the sensor so we can miniaturize it as small as we can. So here you can see it in the size of a fingertip. But we were able to then further miniaturize it by 1/10 of that, which basically is like 5 millimeter diameter. I'm not actually showing this in the slide. And the way this works is that it has all these channels. There you can see here. We fill them with water that we dye black. And then we can basically move the camera off the sensor in a different table, and the camera monitors the water moving up and down in these tubes. And by doing some thresholding and computer vision techniques, we are able to understand if an object is there, what is the diameter, geometry of the object. And also we can do this because it is, again, pneumatically actuated, this sensor. We can also look at different depths, and we have been able to map a tissue that had nodules embedded in it at depth of 20 millimeters, which to our knowledge is probably the deepest that has been done in the literature so far. So how does it relate to dexterity and manipulation and teleoperation? Really is because we want to attach it to grippers. So here you can see one of our bio-inspired biomimetic grippers that we developed. And we named it Lotus because it takes inspiration from the lotus flower, how it opens up and closes, and also how compliant its petals are. Again, we looked at applying this breast diagnosis or examination, but essentially it's a gripper, and it can be used with these sensitive tactile sensors at its fingertip here for any teleoperation task. And we also tried a different type of mechanism, which we call iris, because it mimics how the iris of the camera opens and closes. And it's a very simple mechanism. It's only 2 degrees of freedom, but the symmetry basically makes it so that it can, and the compliance that it has, it makes it able to grasp and manipulate different objects that are asymmetric, of different sizes. And it's also parametric, so you can make this mechanism either with as little as 3 fingers up to 7 fingers. And here you can see a version of it with 5. So I did mention that the title of my talk would be bringing the end user into the research and having the end user in mind. So all of these developments specifically for the breast health and breast examination were done with a series of focus groups with panels. So basically we invite participants, the end users of our devices, to come and see what we're doing, give us feedback. And then we do that regularly every 3 months in our projects. And based on the feedback we have another cycle of research and printing and testing, and then we show them again. So we've done this in the distance of about 18 months, 4 different times. And we have been reporting results, obviously, and based on that, we have developed. And interestingly, we always give them different samples to touch and feel, see what they like, and they give us, you know, like, we like this because it looks more organic, it looks soft, it looks safer. But in the end user really cares about the functionality and the accuracy and how well that, for example, would be compared to a human doing it. So this is a major takeaway here. So moving on a little bit to the extreme environment. So we have been looking at nuclear and space, and specifically for glove box teleoperations. So this was work of my student Kat Stiles, and it was all about optimizing the path planning of redundant robots. So in her case here, she used a KUKA Iowa with a 7 degree of freedom robot, and she also attached a gripper to its end. And it was all about creating this huge database that should be able then to simplify path planning and make it work in real time. So she produced a database that had 1 billion configurations that the robot could then just scroll quickly and pick from them what it needed to be able then to go from a initial position to a target position without conflicting with its glove box, which was basically the constrained environment. So you can see here, going to a complicated path, having no collisions either with itself or with the glove box, which you can't see it now, but it takes the limits of its walls into consideration. So we are looking also at human-robot interaction, especially its trustworthiness. And the application here is in space, and especially when we have latency, high latency. So this is work mainly with my brilliant PhD student, Joe Lucas, and also work with Thales Space UK. So we have been looking at how haptic feedback can be beneficial in high latency operations. So this is where we started, and the results actually, they were a little bit unexpected. It was really interesting because we were expecting haptic feedback will solve everything, it will mitigate all the problems we have. But we started with this little user study here. We had different tasks, basically draw a line with the robot and then place an item in a hole, and do that with haptic feedback, without haptic feedback, or with both visual and haptic feedback, and see how it helps. And what was really interesting is that we saw that haptic feedback actually improved the results up to a point of latency. And after that, it made it so much worse, which was not exactly what we expected when we started this study, but it was really, really useful result. And it was all about basically the miscommunication of the user we thought they were at a specific point, and then were trying to do something, and then suddenly the system was at a completely different point, and it was basically kicking against what it was doing. So this is actually now in print, I believe, probably will be out in a few weeks, this study. But basically, this all we started thinking of, we really need to dock down to the end user. We really need to see what it is that they're experiencing. So again, the end user in mind. And we actually conducted 12 interviews for the 4 different application areas: underwater, explosive, ordnance disposal, and nuclear. And we also included surgeons because, again, they're using very similar techniques. And well, not the same systems, but teleoperation. So we focused on high level requirements of what the priorities are, medium priority, and then also the ones that they will not have. And I'm not going to go through all of this, but just a few interesting ones. They don't really like VR headsets, which was really interesting. They don't like it when a system is controlled by a virtual representation, and the system must be capable of changing the end effector tool automatically. The system provides haptic feedback. It depends on the system. The surgery, they really wanted it, but when you have latency, that creates problems, as what we saw in the previous experiment. And moving on to the more high priority, is basically they talked about the organization basically trust there a lot, and it was all about if your organization, if your company basically approves of a system, then the end user tends to approve of that and trust it as well. But it was all about, again, having a lot of training, having a simulation that they can train, and then with the increasingly risk and realism in that simulation. So finally, and this is the last project I'm going to show, this is, again, very, very new work. It was just accepted, and probably in a week or so will be available. So this is where we looked at Pereira's and Schmidt's model about simulating lunar regolith, and we tried to extend the model to make it more scalable. So you can see here, how the LMS1, which is the simulant for lunar regolith and sand, and then macroparticles are falling through funnels in Earth and Moon gravity. And we tried then to extend the model, make it more scalable, but also we looked at experimental verification of it in the lab in the form of funnels, where we changed the diameter of the funnels, and we looked at the different diameter also of the particles. So we used ball bearings, we used sand, and we also used the simulant in the lab. So what was the main advantage of this model over using other virtual representations that already exist in the literature was that it is lightweight enough to run in real time. So this was the goal, to make it simple to run in real time. And it's good enough for most. It doesn't really scale perfectly for the different angles of repose, and it doesn't work very well when the macroparticles were blocked in the funnels. But depending on what your requirements are, you can use these, or you can use a more computationally heavy model that exists in the literature. So next on this is looking at how accurate is the model when we're looking at more high-level teleoperation tasks. For example, pressing down, dragging the end effector through the regolith, or scooping it and pouring it. So I think that was my last slide. So thank you very much.
Thank you very much, Tonia. We have last 2 minutes for any questions. So if there are any questions, please either use your mic or drop them in the chat.
Radhika, I see that in the chat there is an about the publication. I can put it in the chat. Let me put that. Let me find that.
Yeah, it would be great. Any questions from the audience? Okay, I'll have one. It's on the topic that Radhika raised. It's interesting to see results of those interviews. I didn't note it. How many people did you have a chance to speak to, and what was the breakdown of kind of industry sectors?
Yeah, so we wanted more than that, but in the course of at least 18 months, maybe a little bit longer, we managed to do 12 interviews in total, and there were 4 people from the nuclear reactor maintenance, 3 from underwater exploration and maintenance, 3 robotic explosive ordnance disposal, and 2 surgeons. Okay,
that's quite diverse group. Yeah,
it was
very interesting.
It was length interviews, and we focused more on the qualitative results really than the quantitative on this one.
Okay, thank you very much, Tanya. Is there any last question? Because we are pretty much out of time at this point.
Quick question for me to Antonia. Thank you for the great presentation. with regards to the high delays, are you looking at further research to kind of define where, for different systems, where the delay might be more detrimental than not having it at all in terms of haptic feedback? It's a kind of a topic of high interest for me, because we're definitely looking at, you know, what is acceptable delay for our users, and when we're designing a system, what is acceptable delay, what is not. When is the cost of it just too much because it's just not worth it? So
Yeah.
is there a follow-up research on that?
Yeah, so thanks for the question. I very briefly, brushed over all of these really. So we're still looking into this. And I think that the way you implement haptic feedback also makes a big difference on this. So in our tasks that we did for that user study, we found that haptic feedback reduced accuracy when the delay was 2.6 seconds or more, for example. But it's all about trustworthiness, as I mentioned. So we want to say that what are the effects that it has on the user as well? Will the user's trust improve using haptic feedback, or decrease? And this is also, we continue to look into this, and we want to bring all of this together. We want to look at the regolith simulation and experimental results. Now we're moving into Teleoperation, and we're going to continue to use haptic feedback. So this definitely is work in progress still.
Thank you very much, Tonia. We are out of time at this point, but thank you very much for participation. Thank you very much to our speakers for 2 great presentations. If there are any questions, any feedback about the session with the topic group, please reach out to myself, Alois, or Daniel. And thank you very much. Have a great rest of the day, all.